Another thing I'd like you to get out of chemistry class, Chem 3A, is learning how to think in a more scientific way. And this can benefit you in many areas of your life. So we're going to talk about the scientific method, how chemists think. The scientific method is not a rigid procedure of first we do this, and then we do that, and then we do that. It's really more of a guideline, a guiding idea, a process of doing things. And it emphasizes that observation and experimentation are what lead to learning. So we observe things and we experiment. And this is very different from the ancient Greek philosophers and the philosophies. They emphasized reason. And so they just would sit around and think about stuff. And they came up with some really interesting and what we would consider wacky ideas. Well, I think this. And then they would debate. Well, I think that. But they didn't test any of their ideas. They just thought about them. And thinking about it doesn't make it right. So modern science emphasizes observation and experimentation. There's 4 key characteristics to the scientific method. So the starting point is observation. And observation can lead to laws, and observation can lead to a hypothesis. And we'll talk about all these in more detail, but this is kind of the big picture. From the hypothesis, we test it using experiments. Sometimes that will confirm the hypothesis, or it may cause us to revise the hypothesis, and sometimes we go around in this little loop multiple times. The experiment can confirm a law. We can test laws with experiments and go around in here. After the hypothesis has been tested, it goes to a theory. Theories are also subject to testing by experiment. So that's kind of the big picture. But the first thing we do is it's an observation or a measurement. Sometimes this observation is just something that you see. Other times the observation or measurement may be something that requires some very specialized equipment to determine. But it usually involves measuring something, how heavy, how fast, how large, or a description of some aspect, its color, or something like that. An observation. As an example, your book talks about an experiment that Antoine Lavoisier did back in the 1700s. So he was studying combustion, burning of stuff. And he would burn things in closed containers. So he'd put a chunk of wood or coal or something into a closed container and burn it and see what happened. His observation was that the mass of the container and its contents didn't change. This was really interesting. Because think about a log in the fireplace. You put it in there, it was heavy. And you have your nice cozy fire on the rare time when burn days are allowed. And then later, what's left? Ashes. Do the ashes weigh as much as the log did? No. What happened? Where did that stuff go? So Lavoisier was interested in these ideas. So he burned something in a closed container. And what he found was that the closed container with its contents weighed the same before and after the object inside had burned up. That's the observation. Observations lead to the formation of hypotheses. A hypothesis is kind of like an educated guess. It's a, I think that. It's a tentative explanation. Well, maybe this is what's going on. You're not for sure. You don't know for sure. You're just saying, I think this is what happens. A good hypothesis is falsifiable, meaning you could test it and prove it wrong. In the example, Lavoisier hypothesized that combustion involved the combination of a substance with a component from the air. So he said, okay, this wood is burning, and it must be combining with something from the air, and that's how it's still weighing the same afterwards. And it's in a closed container, so everything's still in there. That was his hypothesis. We test a hypothesis with an experiment. Scientific experiments are highly controlled. We look for all the things that could be changing, and we try to control them. And so if we're going to do his experiment over and over again, we may use the same type of material in the same kind of a container, and we're going to test it, and we're going to do it the same each time. So an experiment is designed to validate or invalidate the hypothesis that it's testing. If the experiment shows the hypothesis to be incorrect, sometimes we're able to just modify the hypothesis, and other times we just have to throw it out because, wow, that was really off. If we revise the hypothesis, we have to test it again. No, not hitting the button. Come on, there we go. When we have a number of similar observations, that can lead to the development of a scientific law. A law is a brief statement that summarizes what happens. It's like, if we do this, this will happen. You're familiar with the law of gravity, right? It states what happens, doesn't state why it happens. In fact, scientists are still kind of arguing about what exactly is gravity. But laws can predict the future. So here I have a pen. If I let go of this pen, the law of gravity says what's going to happen? It's going to fall. Oh, look, it did it again. Every semester does the same thing. Why? I can't explain that to you. But gravity pulls things towards the center of the earth, right? That's a law. It says this will happen. This is what happens. We don't have to actually understand what's going on to develop a law, but we make a lot of observations, we observe the same thing happening, and it becomes a law. But laws can be tested experimentally. I just tested the law of gravity. It's still in effect. So, take the stairs, don't jump off the balcony. It's a big step down there. So in our example here, from his experiments, Lavoisier developed the law of conservation of mass, which states that in a chemical reaction, matter is neither created nor destroyed. So he burned something in this closed container, and the mass of the whole container didn't change. It was a chemical reaction, but the mass didn't change. So that meant that the matter was not being destroyed. When you burn a log in the fireplace, you're not destroying matter. You're converting it into different forms. And a lot of it is gases that go up the chimney. But it's all still here in the universe. If we have well-established hypotheses, that can lead to a scientific theory. Theories and laws are different. A law says what happens. A theory tries to explain why. Okay, so law says what, theory says why. So theory is going to provide an explanation for the observations, an explanation for the law. It's a model of the way nature is. And we can use it to predict behavior. Theories work better for predicting behaviors than laws generally do. Oftentimes it will predict behavior beyond the observations that we initially had that developed them. Again, subject to experimental testing. Scientists tend to be very, very skeptical of things. It's like, okay, so you did that 50 times and it worked for you, but I'm going to see if it works in my lab on the other side of the country. And, okay, well, you did that 100 years ago. Let's do it again and see if it still works. And we test things over and over and over again. So Lavoisier's law of the conservation of mass later led to John Dalton's atomic theory. that all of matter was composed of atoms. And we'll talk more about John Dalton's theory later. So, comparison of laws and theories. Law says what happens, arises from observations, can be proven false. Theory tries to explain why. Theory arises from hypotheses. A hypothesis, remember, is an explanation, why is this happening? Theories can also be proven false, but a theory is as close to truth as science can get. It's kind of hard to get your mind around, but we can't prove something to be true. We can prove it to be false, but you can't prove it to be true. So accepted laws and theories, we accept as truth, just understanding that we have not figured out anything that contradicts them yet. And some theories, some laws that were understood for a long time to be true, when we gained more understanding about the natural world, we found out that they weren't entirely true. So we should be able to identify if something is an observation, a law, or a theory. So this first one, when a metal is burning in a closed container, the mass of the container and its contents does not change. Is that an observation, a law, or a theory? That's an observation. So O, observation. B, matter is made of atoms. Theory. A theory explains why and comes from hypotheses. Can we directly observe that matter is made of atoms? We can't. That's not an observation. It's not a law that says what happens. It's actually an explanation. That one's a little hard for a beginning student to get. Matter is conserved in chemical reactions. I hear little mumblings. Somebody be bold. It's a law. It says what happens, not why. Matter is conserved. When wood is burned in a closed container, its mass does not change. Observation. So that can be a little tricky. If I give you one of these on an exam, I'll try to choose one that's a little more obvious. These are not super obvious. Any questions about those? Yes?
So theory is what happens?
A law is what happens. Theory is why. If it helps, think of the law of gravity. The law of gravity says what will happen? The pencil will fall. Doesn't explain why. Why do two objects experience a gravitational pull on each other? Just because they have matter. Why? Scientists are still arguing about that. Any other questions? Are atoms real? Yeah, we're pretty sure they are. This is an image with the kanji characters, these are Japanese characters, for atom, written with individual iron atoms on top of a copper surface. This was taken with a scanning tunneling microscope, which is a very expensive, complicated piece of equipment. And that's about the best picture we can get of atoms. They're pretty fuzzy, even if you're looking at them on a good resolution screen. They kind of look like cones, but that's just an artifact of the instrument.